So we're going to look at an example of an external torque creating a change in the way an axis points that is consistent with the right angle. Okay. Question so far?
Can you say everything but slow?
Sorry.
Just play the video at 0.5 speed.
I'll say it again. The question was, what's torque anyways? I said torque is the cross product of moment, arm, and force. If that's true, torque has got to be perpendicular to both moment, arm, and force, which implies something that's like kind of weird. Like you open the door, the torque is along the axle. I push the door this way, the torque is up. That's ridiculous. Okay. If torque is what we think it is, it should create changes in angular momentum, which for our purposes today will be not changes in spin rate, but changes in spin direction. So we're doing an experiment today to show that if there is an applied torque, the way the angular momentum changes have to be in that direction. Okay? Okay. So here's the system. The system is our bike wheel friend with a string attached. And I don't mean like a metaphorical string attached, I mean a literal string attached.
So it has
That wasn't the metaphor. Okay. What I mean is it's not strings attached. That's it. Forget it.
I got it.
So here's the question. If I take this wheel and I drop it, right? That's just evidence that there is gravity. Okay. And as you know now from your you giggle, but it's going to get real complicated real fast.
That's not what I was laughing at.
Sorry, my bad. If I drop this thing, that's just evidence that gravity is pointing down. Now, as we know, gravity acts as if this entire body is located at the center of mass, which, because this is a highly symmetrical object, we can pretty much assume is at the geometric center. So it's going to be along this dimension, and it'll be along this dimension. So it's like right at the intersection of those two dimensions. No surprise there. The geometric center of this is where the center of mass is located. So that gravity vector is pulling straight down. Now, if I drop it, it falls. But if I don't allow it to fall, rather I constrain it with this string, it starts to like do that. Yeah? Now, it turns out that this in and of itself can be thought of as supplying a torque, right? Because there's like this tendency to rotate about that point. So let's treat that as a torque problem and see what comes out.
Wait, would the torque be changing?
Yes, it would be. But let's just talk about the instant that we notice it. All right, so here's my system. I've got a torque, I've got a point of contact, and then I've got this handle, and then I've got a wheel, and then I've got the handle coming out again. You're smart enough to draw this, and I'll tell you why. It's going to be hard to draw.
Josh is down.
And if I were to draw the forces involved, they would look like this. I would say mg down. I've got a tension arrow up. I'm going to leave that out of the picture for simplicity, and also when I'm going to compute the torque, I'm going to treat this as my new axle of rotation. So I've got two axles of rotation here. One for the sort of bulk motion of the wheel, and the other is the spin axis. Okay? But the point would be that that's how I define my moment arm. My moment arm is the distance between there and there. Yeah? The distance between this axis of rotation and the point of application of the force. There, that's the center of mass. Okay. So, what should the direction of this torque be due to gravity acting over that moment arm? It should be into the board, okay? So you take your fingers, point them along the direction of the moment arm, curl them down because gravity is down, and the torque should be into the board. It's gonna be a little tricky to draw, but we can make an attempt. Now, just to make things clear, I'm talking about a 90-degree angle with the moment arm, and I'm talking about a 90-degree angle with energy. So implicit in this picture is my fancy sort of geometric plane. Right? Except now I've got, rather than a force going into the board, I've got a force going down. And oh, check it out, I just rotated the torque 90 degrees. Okay. All right, so fair enough. I do this, yeah, and I'm claiming that the torque is this way. This doesn't show us anything, right? And the reason why this doesn't show us anything is because there's no angular momentum in the system. Okay, so if I put angular momentum in the system, for example, if I start to spin the wheel, the angular momentum of the system here should be along this axle. Why? Because omega is also along that axle. And angular momentum and angular velocity are just collinear and scaled by moment of inertia. Okay, so if you have an expectation that torque and dl are on the same direction, what should the future direction of L be?
Into the board.
Well, let's say that this is my L vector. So the wheel is spinning, got an axle. If there's a torque like this, the delta L should be like this. Therefore, the new L should be like that. Yeah? Now, the new torque is like this because the moment arm moved in space. So the moment arm was like this, but now the moment arm is like this. So the new torque is perpendicular to the moment arm. Gravity is still down. So we get this, right? And then we do this again and again and again and again. So what I'm claiming is that if I spin this wheel,
Can you repeat that one more time?
yeah. This represents the axle of rotation of the wheel as it spins. So not only is this the physical axle, but this is the vector direction of angular momentum. An arrow pointing that way, because I'm going to spin the wheel towards you. Okay? So the vector direction of angular momentum is that way. The torque is not in the direction of angular momentum. Torque is in the direction of the time rate of change of angular momentum. So if torque is into the board, the change in momentum is into the board. The new momentum will be over here. Okay? Now R changes direction again. The new change in the new torque is like this. So now the momentum will do that. And that. So we would expect this wheel, rather than falling down, to do this, which it will. Okay? Let's see if that works. So I'm going to say, here's my follow wheel, right? And then if I spin this thing, like this, so the angular momentum is pointed that way, and then I just say, let it drop, and it does that. Okay?
Oh my
No way.
no.
All right, so what you're seeing is the direction of the torque as this thing tries to fall. Okay?
And it's not even like dipping at all.
Okay, so actually, this is a really nice example of what angular momentum is. Angular momentum is, just like regular momentum is like resistance to force, angular momentum is resistance to torque, so the angular momentum is like, I want to maintain axial orientation in space, so I'm going to try really hard to resist this torque. Okay? So this motion has a name. This motion is called precession. Precession is what happens anytime a spinning rigid body with mass is put in a gravity field. Okay? Anybody think of examples of spinning things in gravity fields?
Like planets.
Planets. So the sun exerts a gravity field, or has a gravity field, the Earth is in it. Indeed, the Earth's axle precesses, so like let's say that the sun is way over there, Earth's axle will do this. The period of this oscillation, by the way, is 23,000 years for the Earth. So right now, like let's say that that's the North Star, Earth's north axis is pointing there. So in half of 23,000 years, the Earth's axle will be pointed away from the North Star to a totally different star, and then in another 13,000-ish years, it'll be back.
Wow. So
Yeah.
climate change is not man-made.
Exactly. Other examples of spinning bodies in the gravity field. So a top, like the toy.
Oh,
top.
yeah.
Like when you put a top on a desk, like for instance, this book. See how the top will start to do this? That's precession.
What if it's like Inception, and you're in like a dream world? So
Wait, why can it balance so well?
It balances because its momentum makes it want to maintain its axle.
You know what I'm talking about?
Kennedy, can you do a 50
Yeah,
hours?
from the top.
No.
Okay. Its momentum wants it to maintain its axle, but that. So just,
It's very hard now.
I don't know, can you guys see that it's doing precession, but it's also doing something else?
It's like,
It's like
making a flower.
Yeah, actually, there's a second motion encoded in here. It's called nutation, and nutation is not something we're going to study, but it's really pretty amazing because like if we just had precession here, we would expect a nice circular trace at the tip of the vector, but actually it's making a little flowery kind of thing. That little added motion is something we're not going to study. Pardon me?
Why does it?
It has to do with the forces that are being exerted by like my hand or the desk and stuff like that. Okay, so let me just kind of summarize here. We expected torque to be perpendicular to moment, arm, and force. We then said a way to observe that would be to look at how torque and changes in angular momentum would be in the same direction. And sure enough, if a system has angular momentum and you exert a torque on it into the board, the angular momentum changes direction. But then the lever arm changes direction, which means that the next future location will continue to do this circular precessional motion. Okay, so yes, in fact,
Wait, why does the angular momentum change direction?
because there's a net external torque.
What's the net external torque?
It's due to gravity. Okay, great question. Why does the angular momentum change direction? Well, why does any momentum change? Because of net forces. So angular momentum changes because of net torques. Okay. So yeah, the torque is actually
Holy.
perpendicular to moment arm and force. Yeah, and it is, if you're thinking deeply about it, it is kind of a holy crap moment. Because you're like, I thought it was just math, but actually no, it's physics. It's like the physical world. Okay. Here are some technological applications for spinning bodies. Anything that you need to have axial stability involves putting a spinning thing in it. So satellites, for instance, as you know, satellites fly around in space. Space is either microgravity or things are in free fall. There's no like gravity direction. So how does the space telescope point itself? Spinning things. So you have, and just so you know, for those of you that are really, really into technology, the gyroscope chips in your phone, they're not actually spinning bodies. So how one makes a digital gyroscope is like a really interesting but totally different question. But the way that you make a gyroscope for a spinning, for a space telescope is you You take a spinning thing, you put it on one axle, take a second spinning thing, put it on a perpendicular axle, take a third spinning thing, put it on a third axle, and you've got an X, Y, Z coordinate system in space. And then you'll have a redundant set of backups. And then once 4 of those gyroscopes fail, your space telescope can't point. Okay? Which is why the Hubble Space Telescope, for instance, has to get serviced by astronauts. They go and they replace the pointing gyros.
Can you hit it again, just so we can see it again?
Yeah. If you have 3 spinning axes, 1, 2, 3, you basically can put a spatial, three-dimensional coordinate system in space. So that anytime like the telescope moves, it will interact with the gyroscope and experience a counter torque along that axle. If you are into fancy boats, there is a product called a hull stabilizer. It is a spinning mass driven by a motor that sits in the bottom of the boat, so that when a big wave comes along, your boat is like, I'm not going to tilt over. Why? Because I have axial stability due to a giant rotating mass in the bottom of the boat. Prior to the global positioning system, people have wanted to destroy the world.
Oh, cool.
People have always wanted to destroy the world, and prior to GPS, the question is, how did ICBMs get guided? So intercontinental ballistic missiles, prior to global positioning, we use something called inertial guidance. Inertial guidance systems are essentially gyroscopes in the warhead, right? So you would put on the top of your missile a spinning system, right? So if the body of the missile would do this, there would be an axle defined internally by the rotating system to tell the electronics that you're off course.
Be careful not to stick a ruler into the spokes of the wheel. Speaking from experience.
Try that.
That's sort of that's the physical idea behind inertial guidance. Anyways, gyroscopes are, they're technologically interesting. Things like stability on bicycles, stability on motorcycles, like counter steering on motorcycles. Anybody ever heard of this? Okay, so if you're on a motorcycle and the wheels are spinning super fast and they're heavy, right? And you turn like this, the torque involved is along this axis, which means the counter torque on you is on this axis. So actually, if you turn the wheel like this, there is a physical reason for the bike to flip over, right? So actually, when you're on a motorcycle and you want to turn left, you lean left, but you turn right. It's called counter steering. Check it out on YouTube. There's lots of videos. Okay, so we have about 15 minutes left in class. And what I'd like to do is have everybody feel this. Because it's like, you can see this demonstration and kind of get it, but it's really the feeling, the physics of it, the physical feeling. So what I want you to do is take your wheels. You're going to do this, and you're going to, or if you do this, you're going to be like, ooh, it's doing that. Right? If you do that, it's going to want to do this. Okay?
Wait, why?
Because torque. Because torque, you'll feel a counter torque from it. Okay? So